Hello everyone, and welcome to Climate Cocktail Club. We're about to get started, so make yourselves comfortable. Give us a hello in the comments, let us know where you're tuning in from. I hope you have a drink at hand, a cocktail, mocktail, some water to keep hydrated as you learn. If you don't, there's still time. I'll be making one myself shortly. So what is Climate Cocktail Club, I hear you ask? Well, we don't take too much of an introduction. Climate, we create a platform for people to get inspired and act on climate change. Cocktail, our events generally involve refreshments, ideally a cocktail or mocktail. And we're a club. We're all about coming together and collaborating. Whether you're meeting new people or connecting with old acquaintances, 2 heads are generally better than 1, and 100 heads are better still. But congratulations, you've made it into the club. Tonight, we're all going back to school to learn a little bit about climate science. Climate change is regularly talked about, but how well do most of us really understand the science? It's a big and complex subject area. Those at the forefront have spent years studying it, and for those of us who aren't trained scientists, it can be hard to keep up to speed. Whether you're trying to stay on top of the latest research or just catching up on the basics, we hope tonight will help. Now, in the spirit of learning together, we encourage you throughout tonight's event to post a comment, and by comment we mean anything, a reaction, a question, a link to something you think may be helpful. Please get involved. I know our speakers who've given up an hour of their evening will appreciate it. But before we get on to the serious stuff, we want to make sure we're all sitting comfortably. When the topic at hand gets you hot under the collar, you might want to have a nice refreshment at hand to keep cool. We ask those of you following us on Facebook and Instagram to send through suggestions for climate-themed cocktail and mocktail names before picking our favourite. The cocktail chosen to stir up a bit of climate action this evening is the CO2 Old Fashioned, which I'm going to show you how to make now. So what you want to do is take a short tumbler with a few cubes of ice. Nice big cubes if you've got them. You're going to add a double shot of whiskey. And then about a teaspoon of sugar syrup. And then a good few splashes of orange bitters. I'm using orange bitters for this one, but you can use any good cocktail bitters. And then what you want to do is give it a good stir. Now, aside from having good quality ingredients, this is the crucial bit. You want to make sure the sugar is nicely distributed throughout the drink, and that liquor is nice and cold. I think that should do it. And then to top it off, we're going to garnish with a little strip of orange peel. There we go. It's pretty good. So send us a photo of the cocktail you prepared at home, either in the comments on YouTube or Facebook, or on Instagram or Twitter using the hashtag Climate Cocktail Club. And I'd like to take this opportunity to give a quick thanks to our cocktail partner, Pernod Ricard UK, who provided the recipes for our cocktails this evening. Of course, I'm enjoying a whiskey-based beverage this evening using one of their brands, Jameson. At Jameson's Middleton distillery in Ireland, they've reduced their energy and water consumption by 28% per unit since 2012. And they continue to invest in innovation to help improve their sustainability footprint. I've used Jameson Black Barrel for mine, which has been aged in charred bourbon barrels, because here at Climate Cocktail Club, we like our whiskey barrels charred, unlike our planet. We'd also like to thank our global climate partner, Natural Capital Partners, specialists in carbon neutrality and climate finance solutions. Natural Capital Partners has more than 300 clients in 34 countries, including Microsoft, MetLife, Logitech, PwC, Sky, and Ørsted. And they work with projects throughout the world to deliver emission reductions, conserve forests and biodiversity, and build low-carbon sustainable development. So thanks to all our partners for their support, which allows us to keep doing what we're doing here at Climate Cocktail Club. Now, it's time to introduce our brilliant speakers. To start off, we're going to hear from Mark Maslin. Hello, Mark.
Hi, guys. I'm not too bad. I really wish I had your cocktail in front of me now.
I can assure you it's delicious. Excellent. Mark is a professor of climatology at University College of London and author of the book The Human Planet. You may also recognise him from BBC and David Attenborough's Climate Change: The Facts documentary. And Mark is going to give us a back-to-basics overview of climate science.
Yep.
We're then going to hear from Professor Joanna Haigh from Imperial College. Hi, Jo.
Hi.
How are we doing?
Great, thanks. Yeah.
Good stuff. So, having been a co-director at the Grantham Institute at Imperial College London and a lead author of an IPCC report, that's the Intergovernmental Panel on Climate Change, Joanna is going to open our eyes to the world of climate modelling. So, I can see that some of you are dropping comments already, and that's great. Keep them coming. We're going to finish with a bit of time for Q&A at the end. So be sure to fire over some questions for our excellent speakers. So I'm going to hand over to Mark to start us off and tell us a little bit about the basics of climate science. Thank you, Mark.
Thank you very much, Indra. So it sounds very strange to be doing this, because last time I did this, I was doing this with a room full of about 120, 130 people, all with lovely cocktails. So I'm just imagining you all sitting around the world with your cocktails. And I'm hoping very soon that I'll be invited back for perhaps a third time, and I can actually share those cocktails with you. What I want to do for the next sort of 10, 15 minutes is just take you through a little bit of climate science. And I've started off with this cartoon because it feels strange. We're in lockdown and we're worried about the pandemic, but actually there's this bigger wave. There is this bigger threat, which is climate change. And we need to actually put the two into context and understand how coming out of the pandemic can actually help us deal with climate change. So the first thing to stress is that climate change science is really, really old. Eunice Foote showed CO2 was a greenhouse gas back in the 1850s. John Tyndall, in our own Royal Institution in London, actually measured the absorption capacity of the gases such as CO2. And what is climate change? And this is something that lots of people ask me. And what it is just the balance of heat from our sun. So the sun radiates out all this energy, and most of it is in the light. And most of it then hits the earth, and a third of it bounces straight back out into space, off white clouds, off white ice. 2/3 of it hits the earth and hits the oceans. So just imagine you're not in lockdown, you're on a tropical beach somewhere, and you're lying in the sun. That light hits your skin and converts to heat. You feel hot and you radiate that heat out to the surrounding area. That's exactly what the Earth does. So that heat passes back into the atmosphere, and then the greenhouse gases capture some of this heat, hold on for it for a little bit, and then release it back into the atmosphere. And those greenhouse gases, as John Tyndall showed, the most important is water vapor, followed by CO2, followed by methane, nitrous oxides, and then artificial chemicals such as CFCs. Now, the interesting thing is if we stripped all of those greenhouse gases out of the atmosphere, the average temperature of the Earth would drop by 35 degrees. So that would mean an English summer would be about minus 15 degrees, and an English summer would be somewhere between minus 20 and minus 30. So if you think about it, greenhouse gases, good, but there's a sting in the tail. Because Guy Callendar, even in 1938, when he put together lots of weather stations, 147 from around the world, saw that the Earth was already warming up since 1880 to 1938. And he understood that this was because of the CO2 that we were already pumping into the atmosphere due to the Industrial Revolution. Now, of course, we didn't stop in 1938. No, it got even worse. And this is the famous Keeling curve. And as you can see, CO2 has gone up every single year since it was measured in Hawaii in 1956. And we're now at the highest level for at least the last 3 million years. Okay, so completely out of the natural range. And we can see this from the greenhouse gases. So these are measurements of CO2 and methane in the air bubbles in ice cores from Antarctica and from Greenland. And the interesting thing is if you drill down into the ice, you can take ancient slices of ice and you can take out the air bubbles. And in those is ancient air. And you can then measure the amount of CO2. So in an ice age, you can see that it's about 200 parts per million. In an interglacial that we're in, it should be about 280 parts per million. However, we're already over 400 parts per million already. So that's an increase since the Industrial Revolution, about 45%. And we've increased methane by 250%. So what's that been doing? So it's already changed the climate. And I think this is really important. Evidence of change is already there. So if we look at, say, Northern Hemisphere spring snow cover, something that we are really keen on because, of course, that gives the best skiing and the best snowboarding. Bad news there, I'm sorry, for cocktail lovers, because that's been going down since the 1960s and actually doesn't seem to be actually recovering at all. And that's going to carry on with climate change. Arctic summer sea ice is also dropping markedly. And actually, there are some models that suggest sometime later in this century, we might have a summer where there is no sea ice in the Arctic at all. The oceans cover 70% of the world surface, and therefore they can hold a huge amount of heat. And guess what? That has been increasing again since the 1960s. That's been causing the ocean to expand because warm up liquids, they expand, and because of the melting of our glaciers and Greenland and the Western Antarctic ice sheet, we're seeing sea level change of about 24 centimeters since the beginning of the Industrial Revolution. So that's some of the evidence. But of course, everybody knows the temperature curve. So this is the famous temperature curve, and you should always see at least 3, if not 5 different records of groups around the world that put all the data together and actually come up with this average. So 2016 is currently the warmest year on record. 2019 was the second warmest record, but I'm happy to take bets that 2020 might be the warmest or the second warmest on record, okay? So if you want to actually win some money off some of your climate change deniers, give them a bet like that. I reckon you'll probably be quids in. I've also put at the bottom the warming stripes by Ed Hawkins, because graphs don't do it for most people, okay? You need something really visual. And so what he's done is converted the data into just colors. And as you can see here, this is the London temperature, because I'm from UCL, and of course Joe's from Imperial, so we're both based in London. And you can download this for free for any city of the world and every country. And so you can actually then look at your local area and how it's changing. And Ed's done a fantastic job with this. You'll be pleased to know that, of course, this has spawned a whole industry. So you can have a beautiful tie. If you can afford a Tesla, you can get it wrapped beautifully in the temperature curve. You can also have t-shirts. It's not cool to be warm. And of course, if you just want some simple leggings, guys, you can get those as well, okay? So I'm not going to do the modeling stuff. So Jo's the brains and is the smart one. And so she's going to talk about how we model. But what I'm interested in is what they predict. So of course, we have scenarios, stories of the future, because we don't know how much people are going to actually emit. And so here we have 5 major projections. So the first one, the red one, is we don't have any climate policies. The economy is just to let go. Okay, so we're looking at 4 to 5 degrees warming in the future. Remember, we've already had about 1.2 degrees warming since the pre-industrial times. Current policies, if they are stuck to and they work, 3.1 to 3.7. The pledges that were made at the Paris negotiations in 2015 take it to 2.6 to 3.2. And then there are 2 interesting pathways that Jo's going to talk about, which is the 2-degree pathway, because the politicians have held their hands up and said, hey guys, yes, it's important. Guess what? We must actually make sure that we keep the world to 2 degrees. And then there's the 1.5-degree pathway, because there's an aspirational target for the world, which is to try and keep the world below 1.5 degrees. Remember, we're at 1.1, 1.2 already. So what does that mean Britain will look like? So the first thing is that many of you may have relatives who complain about how hot it was in 1976. And as you can see, 1976 was a warm summer in both Northern Europe and Britain. Compare that to summer of 2018, when there was a global heat wave. And actually temperatures were actually warmer in Britain and in Europe than they were in 1976. So we'll be looking in the future for summers like 1976, 2003, 2017, and 2018. That will be the new normal. Oh, and by the way, I am a geographer. I hide in a geography department, so just thought I'd give you a little bit of a pub quiz, as most of us have been doing these under lockdown. This is Dungeness, the only official desert in the United Kingdom. Slip that into one of your pub quiz. No one was going to get it right except you. Okay, so heat waves. The 2003 was the worst heat wave to hit Europe up to now. And this is the distribution of nighttime temperatures in London. Why nighttime temperatures? Well, that is when the vulnerable and the elderly are asleep and therefore are less able to control their body temperatures, and many of them can pass away. It also shows you why, if you actually do really well in your job, you should definitely move to Richmond upon Thames, which is that yellow, quite cool bit, and not be in any of the actual warm spots unless you have really good air conditioning. But there's a really important thing about this, because this brings it back to COVID-19. So this is, for France, the actual average death rates for the last 20 years. And you can see that the red line is the COVID-19 excess deaths. Huge, absolutely, massive. But compare that with one heat wave, 2003, which is the yellow one, and as you can see, the number of deaths were higher per day, but it didn't last as long. But you've got a comparable signal there. So when we're looking at climate change, when we're looking at COVID, we've got to look at similar, and actually climate change is probably going to provide a lot worse effects than the pandemic. So what is the risk of extreme seasons? So you can see 1.5 degrees pathway, 1 in 4 summers will be like that 2018. 2 degrees every other year, and 3 degrees, basically it says 9 in 10, but that's really every single summer will be as warm as 2018. And then you have to think about heat waves on top of that. Extreme rainfall events, we're going to have more frequent floods, 2010, 2012, 2014, and 2019 come to mind. Think of Gloucester, think of Hull. Okay, this is because the warmer planet evaporates more water into the clouds and they dump more water in heavier, more intense bursts. We're also looking at flood risk. Think about London and the possibility of storm surges coming down and flooding London. I have to say, I love this picture. I use it a lot. It's from an ITV program, a docudrama that was actually called Flood. Yes, I know. All of you and I could have come up with a much better title for that program. But the interesting thing is, this is highly unlikely because the Environment Agency has plans to protect London up to a 4-meter rise in sea level. Now, the latest IPCC report says a maximum of 1.3 meters in this century. But that's because there are billions and billions and billions of pounds worth of property worth protecting in London. Unfortunately, other cities, even in the UK, aren't as well thought of or protected. We'll also still get these sharp, cold snaps like the beast from the east. The problem is that climate change has warmed up the Arctic and the Greenland Sea. And then what has happened is the sea ice has retreated. That allows the cold air from the Arctic and from Siberia to whip down every so often, smashing into the east side of Britain, bringing for 2 or 3 days intense cold and snow, which then suddenly melts after the 4th day. Actually, sometimes that melting causes as many problems as actually the cold in the first place. And people perceive, oh, do you know what? Guess what? Temperatures are going to be cold this winter. And actually, it's a warm winter with a very cold snap. So we're going to have to adapt, change the Thames barrier, improve our infrastructure. And so we have a look quickly before I pass over to Joe on what are the actual effects. We're looking at more extreme storms, floods, droughts, and heat waves around the world, and in places that they've never occurred before. We're looking at problems of food and water insecurity, which we can talk about later. And that may lead to mass migration and, in some cases, conflict. So the UN Paris Agreement says that we need to get to net zero in this century. And to achieve this, we must transform our energy generation, industry, infrastructure, and personal behaviours. And this is the challenge that I'm going to set up. And hopefully Joe can then talk about the future scenarios, which is the red line is where we've got to now. And we need to actually, in the next 30 years, hit zero. Okay. Now, after that, we can then have to suck out CO2 out of the atmosphere for the next 50 years to keep the temperatures of the planet to 1.5 degrees. It's technically possible, and we can talk about what COVID and the drop in CO2 during the lockdown, which is actually quite small, tells us about what we have to change to save the planet. So we need win-win solutions, and these are all the things that I've put on here, and hopefully we can talk about later. And with that, I'm going to pass over to Imperial and, of course, Joe. Thank you very much.
Thank you very much, Mark. Interesting, if ironically chilling stuff there. I feel like I've learned a lot there myself already. I hope the rest of you are taking notes out there. Remember, we'll be fielding those questions at the end, so keep them coming. And as Mark kindly said for me there, we're now going to hand over to Joanna to dive into the world of climate modelling. Thank you, Jo.
Well, thanks, Mark, for that, that great introduction. And I've been asked to give you a little bit of a background on climate models, because you've probably heard about them in many different contexts. You might be wondering quite what a climate model is. It's not easy to understand it if you've not been involved in this sort of thing yourself. So a climate model is a computer model. So it's all calculations, and it's based on very basic physics. So even those of you that aren't in love with physics like me, you probably remember from school, you've got things like forces, mass times acceleration, or something like that. And we can use those laws to understand what's happening in the atmosphere. So in that case, we'd have the forces acting on a parcel of air, would be gravity and pressure and the Earth rotating. And you can put that into a mathematical formulation along with equations for conservation of energy and conservation of mass. So you see, this is all very, very classical or old-fashioned physics. And you can express those equations in a format and then put them on a three-dimensional grid. And that picture you've got there is a sort of example of a 3D grid. And the values of the atmospheric temperature and density and wind speed and direction would be on each of those grid points. And then you can solve the equations and you step forward in time and you find out what happens on the next hour or the next day or whatever the time step is that you're using. So it's, in a sense, it's quite a simple concept, but in practice, of course, there are complications. And the complications rather obviously are that the atmosphere and indeed the oceans are not composed of little cuboid grids. And so that the main problem we have is grid size. Now, the climate models that the Hadley Centre, the Met Office use for their standard runs are about a horizontal grid size of, say, about 100 kilometres. And of course, if you look at a picture of a real cloud, you can know perfectly clearly it's not a 100-kilometre cube. And so you've got to express how the cloud is created in a grid size like that. And that comes in with lots of complicated physical parameterizations that go into the model. And similarly, you've got to think about how the model is going to produce rain, how it's going to produce ice, and the interaction between the water vapor and the ice and the rain. And then how it's going to represent that very complex land surface, and all the processes that could go into a general category that could be called sub-grid scale processes like chemistry and turbulence and all those sorts of things. But the models that we use for computing the climate are exactly the same. They are now exactly the same. They call it seamless prediction as the models which are used to forecast the weather. And so a question that I often get posed is this one. If you've got a computer model that's doing the weather forecasts, and you can see it on the BBC, and they have been getting a lot better, the weather forecasts, over the last few years. But actually, if you predict the weather over more than 10 days hence, you're going to actually get into trouble. It's not going to be a very good forecast after about 10 days. So how in the world can you use these models to predict the climate over decades or indeed centuries? And the answer to that question is because climate models aren't predicting precise values. So we're not predicting what the weather is going to be like on a Wednesday in January in 2050 in London. We're going to be predicting what's it likely to be in southeast of England in the winter in that time period. So we're predicting typical values. And a quote that you often hear is, climate is what you expect, weather is what you get. So the climate's a sort of average typical values, and the weather is what you actually get on the day. So you often hear climate models referred to as GCMs, global climate models, or in atmospheric physics jargon, general circulation models. And as I've already explained, they've been developed alongside weather forecasting models. And we use them as sort of as laboratories for experiments to investigate processes in the atmosphere and oceans and what's going on. So you can try and understand particular processes like water vapor feedback. So I think Mark already mentioned that as the climate gets warmer, you get more water vapor into the atmosphere. And then the water vapor can condense into clouds. And then the clouds, of course, get blown around by the wind. And what we want to know is how those feedbacks work. What happens when the surface gets warmer? Is there more clouds? Are there different clouds? And we can study those sorts of things in a climate model. We can also test hypotheses on how the climate system actually works. So if, for example, one thing would be, you've heard about the El Nino perhaps in the tropics. Do we understand how that works and how it might change in the future? And then we can also try and understand how the climate responds to different, what could be called forcing agents. And they might be human-produced ones like greenhouse gases, or they might be natural ones like volcanic eruptions or the sun. So we can do all those experiments in a climate model to see if we understand the natural climate system. And then, of course, we can do what-if experiments. So these would include the sort of changes in greenhouse gases into the future to see what might happen to the climate in different places. So climate models have got more and more complex over time. The way that I described it just now was really how they got developed in the first place, just looking at the behaviour of the atmosphere. And that was done in the 1970s with great success. So the first climate model results that were published in about 1974, I think, predicting what would happen to doubling CO2, said a global temperature of change of about 3.5 degrees. It showed ice albedo feedback near the North Pole, so the ice is melting, so you get more warming. And all those processes were shown by the model in the mid-1970s. But of course, there's a lot more things that are going on in the climate system that weren't involved in those models at the time. And this chart here is just showing some of the things that have been put in subsequently. So what we've got is various processes that get developed what we call offline. So people are working on computer codes to try and explain or describe these sort of factors. And then they get included into the model development. So in the mid-1980s, we got land surface, then we got a properly coupled ocean and sea ice, then we've got atmospheric chemistry, like particles in the atmosphere. Then we've got the carbon cycle and dynamic vegetation and crops and more chemistry. So the Earth system models and climate models that we've got today have all these components in them, which make a better representation of the actual climate system. So we can use the models, as I say, to try and look at the processes and also to understand what's happened in the past. And what we've got here is two panels, and the black curve is the same in both of them, and it's showing the average temperature change between 1860 and nearly the present. And so, as Mark's already described, you've got this global warming essentially going on, where the temperature is nearly 1 degree warmer than it was in pre-industrial times. Now, all those coloured curves are different climate model estimates of what happened. And in the left-hand panel, we've got calculations which only take into account natural forcings on climate. And they are essentially volcanoes and the sun. So volcanoes chuck a whole lot of stuff up into the atmosphere and reflect sunshine to space. And so those little spikes that you can see down here are actually cooler due to big volcanic eruptions. And then you've got changes in solar activity, which also make a very small modulation of these effects. Then the panel on the right has got all the natural things, and it's also got the greenhouse gases. And you can see that without the greenhouse gases, we can't match the observed temperature rise at all. But with the greenhouse gases, the match is quite good. The other important thing to note about these plots is that there's lots and lots of spaghetti here. There's lots of different coloured curves. And that's because in order to get this sort of average behaviour, we need to run lots of model simulations. If you start them off at a very, very slightly different point, so you might change the temperature in Africa or something right at the beginning in 1880, you don't know exactly what it was. You change it slightly, you get a different evolution of the temperature. And each of those spaghettis there is a different simulation of what the climate was doing. So you can see any individual simulation is not going to be precisely correct. But if you take all of them together as what's called an ensemble, then they match the observations very well. And indeed, in both weather forecasting and climate prediction nowadays, we use ensembles of runs to make sure we get a better picture. So climate models are hugely demanding on computers, on computing power. And you know that the Met Office is always asking for more and better computers, and there's different ways that you can use this power up, and essentially there's 3 dimensions here. I've talked about the resolution, the space resolution that you need, and you can go to finer and finer resolution, and you can see there's very, very fine features here in the atmosphere being resolved in this particular model simulation, but that will use up more computer power. Or you can introduce more of these processes like ice and rain and snow and all the rest of it. Increasing the complexity increases the computing demands. Or you can choose how long you're going to do the simulation for, or the number of models, components in this ensemble. And in each of those directions, you'll be increasing your demands on computing power. So you might choose different points on these axes depending on what question it is that you're actually trying to answer. So if we're trying to look and see what's happening in the future, we not only have to predict the climate, which is bad enough, but we have to predict what humans are going to do to it. And this plot is coming from the Intergovernmental Panel on Climate Change assessment report, the last one in 2014. And it set up these, what referred to as representative concentration pathways, or RCPs in the jargon, of different ways in which, and this is particularly primary energy use, was going to come about. So if you look in the year 2000, what was produced in the energy of the world, there's a black component from coal, orange due to oil, and then these other ones in which renewables is a tiny, almost non-existent component at the top. And then you've got these other pathways in which different assumptions were made about what would happen. Not only this is 2100, but also a path time series as you get there. And this one, of course, this worst case scenario is looking at the coal burning being up by a factor of 8 or something from what it was in 2000. So that's quite unlikely, but that was just a what if type experiment. So here's the emissions in terms of gigatons of carbon of each of these RCPs, the green one being the best one, and the blue one being this worst one. And you can see they have different time series until they get to 2100. So that's the emissions. But of course, emissions are not the same as concentrations, and particularly CO2 is a very long-lived gas in the atmosphere. And so if you put some gas into the CO2 into the atmosphere, it'll stay there for about 200 years before it gets used up. So while the emissions may turn down, even in this green best case scenario, the concentrations only very, very slowly go down. So these are the different RCPs. You can see that quite different between themselves. But I now want to quickly mention the concept of the carbon budget. And what we got in this plot is up here is the temperature result that you get from different total amount of CO2 that's been shoved up into the atmosphere. And so what we got in here, a black curve, is the actual historical emissions. So you might be able to see, I hope, these small, the years appearing in here up to 2010, where the temperature's gone up by about 1 degree, and the total amount of carbon that's gone in up to that date is 400 or something gigatons. Now on this plot, you've also got these different RCPs. So the blue one, which is the better of the ones that were shown, by the time you get to 2100, the temperature's got to about 2 degrees here. And then you can look at these other RCPs. And of course, as you go further, as you go to 2100, they've got more CO2 into the atmosphere. So this RCP 8.51, by 2100, it's got 2000 gigatons of carbon. But the very interesting thing about this plot is that all of these lines lie on top of each other. So it doesn't matter how you got there, fast, slow, lumpy or curved or whatever, the temperature that you get in the end really is a linear function based on the total amount of CO2 that's gone into the atmosphere up to that point. So that's a very, very simple thing to understand. You put more in now, you've got less you can put in till you get to whichever temperature you choose. Now I'm running out of time, so I've got to be quick now. So if we say we wanted the temperature to stop at 2 degrees here, we look and see what does 2 degrees mean? Well, it means we've got a budget of CO2 budget of about 800 or something in these units down here. Or if you want to keep the temperature to 1.5 degrees, you've got to stop the budget. The budget you've got is up here, about 700. So it's a very, very easy to understand message. It's come from very, very complex climate model runs, but the result is very simple. You've only got so much carbon you can burn before you get to a particular result. And then I think I can probably finish there.
Great stuff. Thank you very much, Joanna. Interesting stuff again. So we'll get Mark back on and dive straight into some questions from our audience. So one here from Leanne, which I think is aimed at you, Mark. Mark focuses mostly on CO2 and CH4. I'm very interested in the interconnections there, the quickest wins when including other GHGs as well.
So I personally think that looking at some of the other greenhouse gases is a bit of a false economy, because we've inflated them because they do have a much stronger warming potential than CO2, than methane. But actually the numbers that we get in the atmosphere are actually quite small. And really what we should be focusing on is carbon dioxide and methane, which are the major issue for the rest of this century, because it's about burning fossil fuels. And if we shift our ideas to say, well, let's just deal with sort of CFCs and forget about fossil fuels because we can have some quick wins, that misses the whole issue. And the whole issue is shifting away from fossil fuel use to renewable energies and preventing CO2 and methane going into the atmosphere.
Good stuff. Now we've got another question. So one for Joe. What are the main limitations for current climate modelling? What do you see as the next steps to enable even better modelling?
So models have been gradually improving, not only in their complexity, as I described, but also in their ability to look at what's going on in the climate now and into the future. But of course, they're not perfect. And one of the main limitations, I would say the main limitation now, is the representation of cloud physics. Now, you may have heard a lot of talk sometime on the deniers' websites about climate sensitivity, which means how much the temperature is going to go up to in response to CO2. And the climate sensitivity values have quite a large spread from the different calculations. And the spread is pretty much down to the representation of clouds in the models. Now you can imagine it's quite complicated because clouds are composed of tiny little droplets that condense onto particles in the atmosphere. And so when you're going to try and represent those sorts of processes and then the way that the clouds develop with time and get transported around, that is one of the main challenges to climate modelling at the moment. However, there's all sorts of interesting ways in which I thought about that can be improved. One is to what are called embed cloud resolving models into the big climate models. So if you know that there's a particular region where you're going to have trouble representing the clouds, you put in a much higher resolution grid cloud model embedded within that model. And that's something that people are working on. And the other thing that you can do is, as I said before, make sure that you do lots of ensembles, perturbing the parameters that you're not sure about. So the particular cloud physics parameters, perturbing them slightly in these ensembles so that you can get an idea of the spread. So the next steps, I think, I mean, there's lots of things to do, but I think the most important thing at the moment is representation of clouds, and particularly what we call mixed phase clouds. That's clouds which contain both water and ice in the subtropics, just outside the tropics.
Great stuff. Thank you, Joe. We've got another question. So one from Gary. Can you give a 2-minute explanation of feedback loops and the likelihood of occurring? So I don't know whether both of you want to comment on that, and if you don't mind who goes first.
I can do a very quick one because Joe's already talked about one that is inherent in climate change, which is you put greenhouse gases into the atmosphere, they warm up the earth. More water evaporates, you have more water vapor in the atmosphere, which is a greenhouse gas which warms the atmosphere. So you have a positive feedback there. So there are feedbacks, both positive and negative, in all of the climate system. And the interesting thing is that the models that Joe works with are very good at trying to actually resolve those and actually work out how and which direction they're going to go in.
So, yes, so there's the question says the likelihood of occurring. I think we have to distinguish now between what you might call feedbacks, and I think perhaps what the questioner is asking is tipping points, perhaps, because there's a slight confusion in the terminology, and it's probably as much the fault as the climate scientists as anybody else. When you have feedback on an electronic circuit, you know, it gets worse and worse and worse, and it goes off. But when climate scientists talk about feedback, they're generally talking about things that are there all the time, as Mark has described, like water vapor feedback. That's perfectly natural part of climate, and it keeps the climate a nice, warm place for us to live. Another example is the ice albedo feedback. So if you get a warmer climate, it'll tend to melt the ice in high latitudes. Ice is bright, so when you have less ice, the surface is darker, it absorbs more solar radiation, the climate gets warmer, and that's going to feed back on warmer. You also get feedback loops in the oceans. So if you change the temperature structure of the oceans and you change the currents in the oceans and you change the overturning of the oceans, then you get less cold water coming to the surface. That can again increase surface warming. So many of these factors are perfectly natural parts of the climate system. But I don't know whether you want me to start talking about tipping points now, or perhaps you want to wait for a question on that.
I think let's see what we get up next. So we've got one from Caroline Corrigan. It's aimed at Mark. Mark, do you think we're close to peak emissions, or are we still a few years off? And this is one that one of the speakers on our last stream spoke about.
So if you'd asked me a year ago, I would have been quite pessimistic and said we were probably not close to peak emissions. And I would have said that perhaps in the next decade, we might then start to tail off and actually go towards the zero that we're looking for in this century. However, COVID has been really interesting because there's a really good study in Nature Climate Change that showed in April, there was a drop of 17% globally. And over the year, it's probably going to be about 4 to 7% drop in our emissions. The interesting thing is that now, because we're rebooting the whole of the global economy, we can reboot it in a different way. So actually, COVID may have been the shunt, which allows governments to step back and go, now we have to rebuild, let's rebuild in a more carbon neutral way. And so therefore, we might have just hit the peak because of COVID and then dropping down. So I'm mildly optimistic in lockdown, but that could be because I'm just stuck indoors.
Great stuff.
I'm afraid unless we do something very serious, the COVID thing is just going to be a little blip on the CO2 emissions. We've really got to take action. Mark's absolutely right. It's an opportunity. And I'm afraid living as I do in a slightly sort of green bubble, hoping that things will happen.
Yep.
And then you listen to the government talking about subsidies for the airlines and subsidies for roads and all the rest of it, and you think they haven't got the picture at all. So I think all of us together, sorry to get political about this, but we've really got to put a push on the government and anybody else that will listen and is in power to do exactly what Mark says, and that is to reboot the economy in a way that's going to be not only good for the economy and workers, but also is going to save us from the climate change.
But to give you a scary fact to support what Joe was saying, the really interesting thing is that there's usually 100,000 flights every single day. They've stopped almost. We've almost stopped driving anywhere. That's only dropped it by 4 to 7% in a year. And so 2020, even with us almost stopping our normal lifestyle, is only going back to the emissions that we were emitting in 2006. So it's not like we're going back to the 1940s in our emissions. And so it means that most of our emissions are deeply embedded in our energy generation of our 21st century society. And therefore, Joe's absolutely right. COVID is not going to change anything, but our attitude should change, and governments can feel empowered that they can change things, hopefully better for people.
Great stuff. Thanks, guys. And Joe, here's your opportunity. Helena asks, do the models also help to predict tipping points?
So just for people who aren't familiar with this term, a tipping point is where you get to a certain state in the climate and something happens that puts it into an unnatural state, and then you can't get it back again. So as Mark referred to, all the ice disappearing off the Arctic sea ice, that might be a seasonal thing. But if you got to a tipping point where there was no ice at all in the future, or you might find a tipping point in the tropical rainforests, whereby the climate changed so much that the forests got such dieback that they couldn't then regenerate, and then you're then without the forests. Or you could, one that was quite talked about quite a lot is the overturning circulation in the North Atlantic, where it stops overturning, and then in fact, if you saw that dreadful film A Day After Tomorrow, it's very good on the graphics, but it starts off with all sorts of weather phenomena that are associated with that overturning circulation. So these are things that are quite plausible. Another plausible thing is permafrost. So if you start melting of permafrost in regions where that's forming, then you might not be able to get it back again. So do the models predict these things? They do, some more than others, and some of them are easier to understand the processes than others. I don't think you can't predict a particular date on what one of these tipping points is going to have, but what you can say is that they tend to reinforce each other. If you're not careful, you'll get an ocean one enforcing an ice one enforcing an atmospheric one, and so then you get it worse than you started with. So the models can do them, but I wouldn't say that they're very precise, or you couldn't rely on them to do it by a particular date.
I also think, to back up what Joe was saying, you have to also think of two different types of tipping points. There's the ones that Joe and I worry about, which is tipping points within the climate system, but there are actually tipping points in the climate and society. For example, if the southeast monsoons moves by 200 kilometers northwards, Joe and I are just going to say, well, nothing's changed, it's just moved. However, that could miss out whole countries which don't get any monsoonal rain. So that's a major societal tipping point. And so there's lots of tipping points that could really impact society, which us as climate scientists go, well, nothing really changed, it's just moved. So I think you have to be very careful about pulling these two apart. What's going to affect us, i.e. we're going to have a collapse of agriculture in a particular country, as opposed to these doomsayers whereby the end of tomorrow and things like that. And by the way, I won't have anything said against that film, because for a whole year afterwards, when somebody said, what do you do? And I go, I'm a paleoclimatologist. They go, I know what that is. So yes, I like that film.
Great stuff. Well, thanks so much, guys. I'm sure there is a big round of applause going on. Yeah, big thanks to Joe and Mark.
You're very welcome.
Yeah, thank you for your time. And I think that's all we have time for on the questions. But before we go, there are a few extra bits that we'd like to share with you clubbers. We have prepared a little bit of a reading list with the help of Mark and Joanna. If you fancy taking your learning a step further, you can see some of those suggestions on screen now. We'll also be sharing these by email for those of you that signed up. Also, some of you submitted some great questions in advance of this evening's event when you signed up. Hopefully we've answered some of those this evening. However, there were a few that came up a lot, and you can see some of those here. Again, with some suggestions for where you might find some answers to that. So, as mentioned, we'll send all of those links out to you in a follow-up email. I've also been told that Mark and Joe are happy to share PDFs of slides from their presentation, which is great. Thanks, guys, for that. And before we finish, I'm sure a lot of you out there will be asking, well, is there any good news? Well, there are reasons for hope. We have begun decoupling economic growth from emissions. For the past 15 years, economic growth has risen twice as fast as global energy demand, and emissions even stabilized briefly between 2014 and 2016, whilst the economy still grew, which was a first. And as Mark mentioned in his presentation, there has been some agreement on the urgent nature of the situation. The Paris Agreement got all countries to agree to work on limiting global average temperature increase to 2 degrees and pursue efforts to limit to 1.5 degrees. We're also taking to the streets with movements like Fridays for Future, Youth Strike for Climate, and Extinction Rebellion across the world. And finally, we are continuing in a downward spiral when it comes to the cost of renewable energy, making it increasingly cheaper than fossil fuels in many parts of the globe. So a few reasons for hope and reasons not to give up and to keep stirring up that climate action. So as always, please reach out to us with any requests, ideas, feedback or support for our next events. We are a team of volunteers running Climate Cocktail Club, and we always welcome more people to the club. You can hit us up on email, social media, all of that. Yeah, and I think that is it for our second Climate Cast. So thanks again, everyone, for joining in. I know we had people joining us from all around the world this evening, so thank you so much. And for anyone that missed it, if you've got family and friends that missed the live stream, it will be up on our YouTube and hopefully on our Facebook, although we had some technical difficulties this evening. So thanks everyone so much, and we'll see you at the next Climate Cast.